All right. Hi everyone. Welcome to this week's virtual seminar series on Bayesian decision making and uncertainty. Thank you all for joining us. My name is Natalie Mouse. I'm a PhD student at the University of Pennsylvania, and I'm one of the organizers that's hosting today's event. I also want to thank my fellow organizers, Renato, Alex, and Z, for all the work that they've done in helping to put this seminar series together. Before we get started with today's talk, I have a few quick organizational announcements to make. First off, in coming weeks, we've got a great lineup of other speakers. So I want to encourage all of you to check out the schedule for the upcoming seminars on our website. Our website is gp-seminar-series.github.io. And you can join all future seminars either via Zoom or via the YouTube live stream. For those of you who might want to join via Zoom, you'll need to register for our Google group in order to receive an email with a Zoom link for the seminar ahead of time. So if you're interested in joining future seminars on Zoom, you can register for our Google group on our website. And all seminars take place at 1600 UTC on Mondays. That is Coordinated Universal Time. And for those of you joining us on Zoom today, you can ask any questions that you have by just typing them into the Zoom chat. And then the speaker will be able to choose to either pause and answer your questions during their talk, or just hold questions to the end. That depends on the speaker's preference. But yeah, with all that said, it is my pleasure to introduce Sebastian Ament from the Adaptive Experimentation Group at Meta, who will give today's seminar on unexpected improvements to expected improvement for Bayesian optimization. So yeah, Sebastian, the floor is yours.
Awesome. Thank you, Natalie. Right. Let me share my screen. Okay. So today's topic is our paper on unexpected improvements to expected improvement for Bayesian optimization. And this is joint work with Sam Dalton, David Erickson, Max Valandat, and Eitan Bakshi. Now, before I go into kind of the details of this work, I want to zoom out and talk about the big picture. So what are we usually doing as researchers in machine learning, right? We first start with some ideas, some ideation. We have mathematical formulas in our minds. And ultimately, we want to translate those and make use of them with computation. We want to have computers execute our ideas. And specifically, one important step here that is currently missing that I'm going to show is crucial in this entire workflow that we carry out on a daily basis as researchers is something in between. And what is that in between? Well, kind of a pedestrian word for it might be an implementation. And all grad students will kind of sigh once I mention that word. But arguably, something is also missing in that word. And that is, I would argue, a better word for it might be a translation. Because translation implies that the source and target languages, that of math and that of something computers can understand, code, is different. And we need to be aware of the differences as to not lose things in our translation that are actually crucial to the computation and to our ideas. And so now zooming more toward the detail, this is the structure of the rest of the talk. I'm going to give a quick intro on GPs and BO in general, Gaussian processes and Bayesian optimization. I'm going to introduce the problem, in particular, in this case, expected improvements, vanishing gradients, and then the improvements we made to it, or unexpected improvements to EI, consisting of a log transformation, asymptotic expansions, and novel fat-tailed smooth approximations to both the ReLU and max operators. Now, Bayesian optimization on a high level is a class of methods for sample efficient global black box optimization, in particular for those functions that are very expensive to evaluate. And why do we do this? Because we have a bunch of applications that satisfy those criteria where measurements are very expensive. So in machine learning, for example, we can carry out neural architecture search where one observation includes training a large neural network to its kind of saturation point and recording its test set performance. That in itself is a very expensive operation. It might be in engineering. So here, working at Meta, one project we can work on is on hardware optimization for AR and VR devices. Those are optical problems, as well as physical sciences and for example, material science. Here, I've been fortunate to work on a project that optimizes the sustainability of concrete mixtures that are used in data centers. Now, how do we usually carry this out? Well, Bayesian optimizers consist of a surrogate model on a high level and an acquisition function. So on the right, you can see an animation on the top of a surrogate model that iteratively gets conditioned on observations. You see the posterior mean estimate and also the uncertainty that the surrogate has, particularly in those regions that do not have observations. And on the bottom, you can see the associated expected improvement values. And basically, those intuitively trade off between exploiting the knowledge of high function value regions and high uncertainty regions. Right, surrogate models, we usually use GPs, which can, have uncertainty quantification in addition to posterior predictions. And here I'm showing, as an example, a surrogate model of this concrete optimization problem that I mentioned before. For the acquisition function, right, we usually choose the maximizer of the acquisition value as our next candidate to evaluate. So this kind of acquisition surface that you saw before, we usually maximize that to get the next candidate in our Bayesian optimization loop. Here again, one example for EI, just to kind of show one snapshot of this. Here you see the maximizer of EI in orange, this orange cross, showing that it's kind of offset from the best previously observed point, but still rather close to it. And so there it kind of trades off this both exploitation of being close to the previously observed best point and a large uncertainty region. And there are many extensions of this, so it's not just the single objective case. There are extensions for parallel or batch optimization, where you have multiple evaluations at the same time, constraint optimization, cost aware, and multi-objective optimization problems. And the work that we discuss here applies to all of these variants of EI. Now, one problem that actually was already noted in the Blowtorch documentation before we started this work was that acquisition functions are often difficult to optimize, as they are generally non-convex and often flat, for example, EI. So Blowtorch makes use of multiple random restarts to improve optimization quality. And so that was already in the documentation, but and so generally I think well known in the community as a problem. Here we have some quantitative evidence for this kind of heuristic knowledge that generally as you increase the dimensionality and actually also increase the number of training data points for your GP, the fraction of inputs in a search space whose associated EI gradients are zero increases drastically. And so here, basically on the right, you see one example of this where this red shaded region indicates a part of a one-dimensional search space in this case, where if you dropped a initial candidate to be optimized in this region, it would attain zero gradients and would not move at all. So in effect, if that happens, if you drop a point in this region and it doesn't move, what you're doing is in effect um, taking as your acquisition policy the random initialization process of your acquisition function optimization routine. So we call this, for this reason, EI's flat death valley. And we have theory on this, so why this happens, and the specific quantities that are involved in this kind of in this observation. So basically, the values and gradients of EI vanish for objectives that have very highly concentrated high-value regions, and also simply as the optimization routine progresses. And as I already alluded to, that means that if you initialize a candidate in your acquisition function optimization routine to be in that flat region, then inadvertently you're going to give rise to a combination of random search and actual EI search. And that might actually not per se be bad, because sometimes random search can perform very well, especially if your surrogate doesn't fit the data well. But arguably, it's important for us to understand what acquisition policies we're using and do that consciously and not kind of inadvertently like this. Now, I'm going to introduce log EI, this new family of acquisition functions that carefully translates the ideas of EI into a format where it can be optimized much more easily by gradient-based optimization routines. And the key ideas here are computing in log space. Notably, though, we can't simply compute the numerical logarithm of EI, so we need to be more clever. We're going to use asymptotic expansions especially for large inputs to EI, and especially for the Monte Carlo versions of EI. So for parallel EI, for batch acquisition EI, and multi-objective EI, we're going to propose new nonlinearities, new approximations to the max and rel nonlinearities, whose characteristics are that they decay with a fat tail, which is important for numerical stability in this case. So the first idea here, we can just highlight on the simple analytical version of EI, and simply taking the logarithm of this in a clever way is sufficient to make this work well. You see that this log h function here has some special cases, and there's some careful implementation here with these log tricks, log 1 mexp functions that allow us to compute these quantities stably. And this last case here also already uses an asymptotic expansion, which we're going to look at in the next slide. But basically, the high-level idea is for simple analytical EI, we can compute the logarithm of EI in a careful way, and this is usually sufficient. So here we see that if we compute regular EI, the point at which it becomes numerically zero is probably like -10 in its input. Z here being the difference between the posterior mean, the best previously observed point, divided by the posterior standard deviation. And this new log EI function is basically stable throughout all of these ranges. And here, idea number 2 is leveraging these asymptotic expansions. I showed this kind of simple equation in the slide before, which comes from truncating this more comprehensive asymptotic expansion. It's a Laurent expansion of this log h function. And here we can see this convergence behavior of this asymptotic expansion. Basically, the higher we take the order, the faster we converge in this z value, the input of EI. For our implementation that is now in BoreTorch, we simply use the first term because we can evaluate the other terms so far out that we don't need to approximate until a very, very distant point on the negative axis. Here are some comparisons also with previous implementations of the logarithm of EI in Robo and Hebo, both of them being more unstable generally, either because they don't use asymptotics or because I think that there was also some other problems with numerical instability as well. Right, and so here, what does this give us? This is a very simple test function. It's just a quadratic, so a convex function. We see that regular EI asymptotically actually doesn't converge even on this very simple function, which should be a huge red flag, right? We should be, if we hope to optimize non-convex functions globally, ideally we can also optimize a convex function robustly. And so here we see that the problem with EI is that the acquisition values drop off after a certain point. So the optimizer of the acquisition function can't find promising values anymore. But we see that that is not the case for the log EI implementation, simply because the optimizer can move to the high value regions informed by the gradient signal. So here there are some more test functions, again with analytic EI, comparing them the results to Gibbon and joint entropy search. Both are types of entropy search. And here we see that we are sometimes outcompeting Gibbon, for example, and also Jess in certain cases, joint entropy search. Asymptotically on ACLI, you can see in 8 and 16 dimensions that joint entropy search does a bit better. So we stagnate with log EI. I dug into this a bit more, and the problem here is not the acquisition function anymore. It's simply because ACLI is non-differentiable at the optimum point, so that if you really purely rely on a GP surrogate that can't express this non-differentiability at the optimum, at some point, even the correct acquisition values will kind of draw you away from the actual optimal point. I saw that there was some question. Let me see if I can find that. Sorry, was there a question? Here. How much smaller is epsilon value and log expected improvement? How much smaller? I guess I'm interpreting this as how small is the epsilon value in log EI as this point here. That's like numerical precision. So it's like 10 to the negative 16. So very, very small. I hope that answered your question. Let me know if it didn't. Right. So here, then we can generalize this also to constrained optimization. We have the results for constrained log EI. In this case, the improvements are quite dramatic compared to constrained regular EI, which is because the numerical issues basically compound with every potentially numerically vanishing function that you add, right? So regular EI is potentially numerically vanishing, but so are all of the constraint functions. And so the more constraints you have, the more unlikely it is that you will find a point with a good gradient signal. And so these are all engineering related problems, and we see that log constraint EI is generally competitive with scalable constraint BO in red, which is a special constraint method, and generally vastly outperforms constraint EI, which is technically mathematically leads the same policy. Right. Then the third idea here is for Monte Carlo EI. we now smoothly approximate these hard nonlinearities like max and the value. So here, this is basically the formula. Um, the important part here is that we can't just use a soft plus. We also need to first transit everything into log space. So we have all these like log soft plus and log some exps everywhere. And this allows us to keep the computation in log space and therefore maintain gradients all the way through. And this generalizes now to parallel, EI, constraint EI, multi-objective, EI, etc. We also have an approximation guarantee for this, so it's not just some changes to the acquisition value, and we basically have a tight bound on how close the exponent of q log EI is to the original QEI value, and this gets increasingly tight as the temperature parameters of the value and max operators are reduced. Now, the last important idea here is that we define these new fat-tailed nonlinearities. And this is because in log space, even the soft plus in conjunction with these chained log sum exps can give rise to vanishing gradients. And this is because a log sum exp only tolerates an input range of around 700 in double precision before dropping gradients for some inputs. And so this is why we can't actually simply use the log of the soft plus, but instead we define these new fat-tailed nonlinearities. On the left, you see in real space a soft plus compared with the new fat plus in this case. So in real space, there is no visual distinction between the two, but in log space, we see that this fat-tailed nonlinearity decays much slower. And now here we see the results on parallel, noisy, multi-objective log EI. So basically putting everything together, a very complex problem class. And we see that first, that the log version of this, so log q log NEHVI, drastically outperforms the non-log version, but also multi-objective joint entropy search, which might come as a surprise. So here, probably joint entropy search itself, right, can have numerically vanishing gradients as well. But by fixing the computation for EI, we can basically get state-of-the-art multi-objective optimization performance on these problems. One subtlety here is on the bottom right, you see that Q log NEHEI only starts outperforming the other functions, the other policies around, let's say, 200 iterations, and actually is worst between 100 and maybe 180. And this highlights a kind of perplexing aspect of this, which is we can optimize the acquisition function better, but it doesn't necessarily, in all cases, have to translate to better optimization performance. And this is in particular the case for very challenging to optimize objective functions where our surrogate might fit very badly initially. And if we rely on such a badly fitting surrogate too confidently, then even optimizing the acquisition function better does not give us better optimization performance end to end. Nevertheless, while that is true for some fraction of this run, it ultimately the log version outperforms both of the other policies. So here I started with this segment of the Blowtorch docs that said that EI was often flat, and now based on this work, we added that log EI and its siblings, so Q log NEI, the noisy version, and Q log NEHEI, the noisy multi-objective version, can improve this flatness issue and generally lead to significantly higher optimization performance. So in summary, the careful reformulations of EI and translations can improve optimization performance significantly, and the API is basically a drop-in replacement. So whenever you use Blowtorch and use EI in Blowtorch, you can just use the original API and add 3 letters to it, log, and you can take advantage of all of these improvements. So with that, I thank you for listening, and we can open up for questions.
Cool, yeah. Thank you so much. I want to conclude by thanking you for giving today's talk. And really quickly, before we move on to question and answer period, I just want to let you all know that the initial period of question and answers will continue to be live streamed. But after that, we will conclude the live stream. So if there's anyone who wants to ask some additional questions or have some additional discussion outside of the live stream, you can stick around on Zoom for that following this initial question and answer period. But you can go ahead and drop questions in the Zoom chat, and we can also unmute folks who want to ask questions.
Cool. I also see that there is one more question here that I haven't seen before. The question is, any insight into why the performance is so much better than SOTA in the multi-objective setting? Well, I think it's because in the multi-objective setting, as for constraint optimization, you just have many more terms that could potentially lead to vanishing gradients. And so the more terms you have, if you work in the real space, the original formulation, the vanishing gradient problem compounds. So, if you have a 70% chance, or let's be more conservative, a 50% chance of having a vanishing gradient in objective 1 and a 50% chance in objective 2, then you'll much more likely end up with a vanishing gradient for the multi-objective optimization problem than just for one objective. And similarly for the constraint problem, you also add these independent terms. Interestingly enough, I showed mainly these kind of synthetic and engineering benchmarks, but even for the concrete optimization problem that I've worked on, I was actually only able to optimize this with Bayesian optimization using QLog NeHBI. It's also a multi-objective problem with a ton of constraints. And so because it was both multi-objective and with lots of constraints, before with the regular version, I kept on getting no feasible point found errors and other numerical problems. So the more objectives you have, the more constraints you have, the more difficult the problem is, and the more benefit there is to getting the numerics right. Cool. Yeah. Let me know if you have more questions about that or other questions. In the meantime, I do want to highlight if anyone is working on entropy search or other acquisition functions, I'm sure there's a lot of low-hanging fruit there in terms of translating these ideas to other acquisition functions as well. And I'm sure you can get entropy search more competitive as well. And beyond that, right, you can also apply similar ideas to even other problems. It doesn't have to be acquisition function optimization. There are other smooth nonlinearities we use, for example, to parameterize length scales in Gaussian processes. Sometimes we do that with sigmoids, sometimes with soft pluses that can give rise to vanishing gradients as well, leading some length scales to be pushed out very far, and then they can come back maybe in subsequent iterations of a BO loop. So there are lots of numerical improvements one can make, and these ideas are not specific to EI. if you're interested in trying these out. So Alex, your question I think is visible. I thought it was a response to Ashwin's question, but let me just make sure that so your question is, it seems to me like improvement might come from two factors: running the optimization algorithm in log space, minimizing the log of EI, and B, running the numerical computation in log space. Have you tested variants like log of vanilla EI and the exponent? So I've not personally tested this, but I think Alex, some co-authors of yours in the Gittins Index paper on cost-aware optimization, you ran really insightful studies on the difference between what kind of the numerical log would do in terms of improving the optimization performance and what the benefit is of kind of the numerical computation itself. That led to, if I recall correctly, even some improvements for taking the numerical logarithm. And I suspect that that has to do with the optimizer terminating the optimization, even if some gradients are numerically non-zero, but below some threshold, right? So optimization algorithms usually have some thresholds in terms of the progress that they make. And just taking the numerical logarithm can already lift all of the quantities above that threshold and improve the performance, but doesn't fundamentally change anything when you really go into a zero gradient and zero value region of EI. Does that answer your question? So that was my interpretation basically of those results. It's like the numerical logarithm basically helps avoid the non-zero optimizer thresholds. And then the additional net benefit you get from the numerical log space um, is that you can lift like even things that are numerically zero before uh, out of that.
Cool. Yeah, we're gonna go ahead and conclude the live stream now. But before we do that, I want to thank all of our listeners on YouTube for joining us today. And remind everyone that we have another seminar coming up next Monday. So again, you can check out our schedule on our website. That's gp-seminar-series.github.io. So feel free to join us next week. Thank you all. Um, and then just give Alex a second to actually turn off the live stream.